So welcome back again. Let's take a look at our concept check questions, and then we'll talk through the last section for this chapter. If two parents are carriers for albinism, what are the chances of their fourth child being albino if their first three are normal? The answer is 1 out of 4, and the answer is always 1 out of 4. And the reason why is because the Punnett square does not change just because a child has been born with a particular genetic combination. So if we do the Punnett square here, let me just make sure I've got the pen up. Oops. One. So here's our Punnett square. Albinism is a recessive trait, so it will be little a. And we're told that both parents are carriers, so there we have their genotypes. So there's our albino child. It turns out that having a child does not change the Punnett square. So it's the same Punnett square for each child. It just so happens that for this particular couple, their first three children lay in this group, either homozygous, dominant, or heterozygous. They were just lucky. Remember, this is all about a flip of the coin. It's just probabilities. So the fact that their fourth child could potentially be albino is still 1 out of 4, irrespective of how many children they've had that are normal. The odds don't change. The probabilities remain exactly the same. What is the probability of a child inheriting a dominant trait from their parents if only one of the parents has the condition? 1 out of 2, 50%. It's the Huntington's disease question, or the achondroplasia dwarfism question. If a parent has one of those dominantly inherited conditions, they have a 1 in 2 chance of passing on the allele. That's the minimum chance of passing it on. Of course, if they are homozygous dominant, which would never be the case in achondroplasia dwarfism, and I believe it's not it's also the case in Huntington's. If it's a homozygous dominant embryo, that's also a lethal condition. So an individual with those conditions would be heterozygous. It's a 1 out of 2 chance of passing it on to the child. So when we start thinking in terms of inheritance patterns, as tempting as it might be to say, well, Mendel's 2 laws explain it all, the short answer is no, not at all. In fact, the longer answer is that Mendel's laws only apply under very, very certain circumstances. There are very specific conditions that need to be met in order for Mendel's rules to actually apply. So when we start looking at inheritance patterns in general, what we notice is that there is a number of inheritance patterns that seem to align with our understanding of Mendel's genetics, but actually are not covered by Mendel's 2 laws. So let me talk about a few examples here. So the first is this whole notion of dominance. In Mendel's genetics, one trait is always dominant over the other, and it's complete dominance. So the purple trait is completely dominant over the white trait. If an individual is homozygous or heterozygous for purple, you only see purple, and there's no variation on it. And that's because the purple trait is truly dominant. But here we revisit the snapdragon question, because here we have this observation that when you breed a red snapdragon with a white snapdragon, you get pink. The geneticists of Mendel's day said this is blending because they stopped with the F1 generation. But as we know from Mendel's work, you really need to get the F2 generation to fully understand what's going on. And if you breed 2 of the F1s, these pink snapdragons, what you find is, unlike what you might predict if you actually had created a pink allele by blending the red and the white alleles together, which ought to give you pink flowers. What you actually get is pink flowers, yes, but you also get red and white flowers. So what is it that is actually blended here? It's obviously not the alleles. It's not the red allele and the white allele blending together to get a pink allele. Otherwise, we'd have pink flowers. What's blending is the pigments, because here, the white allele So the pink flowers are simply the blending of the red pigment and the white pigment, what I was talking about back at the beginning, mixing red paint and white paint together to get pink paint if you needed pink paint but didn't have any. So here, it's not the alleles that are blending. The red allele and the white allele remain discrete, as Mendel would predict. What is blending? The pigments. This is an example of incomplete dominance, where the red is not completely dominant over the white. If it was completely dominant, you would see red flowers in the F1, but you see pink. And that tells you that you've got incomplete dominance. And there are two things that you ought to notice about the F2. The genotype ratio can write this out correctly. So the genotype ratio here is 1 to 2 to 1. 1 big R, 2 big R, little r's, 1 little r, little r. The phenotype ratio is also 1 to 2 to 1. 1 red, 2 pinks, 1 white. And this is indicative of incomplete dominance. Remember, if this was Mendel, the phenotype ratio should be 3 to 1, but it's not, it's 1 to 2 to 1. So if you are given some numbers in an exam question and the ratio of genotype, the genotype ratio and the phenotype ratio are both 1 to 2 to 1, you know you're dealing with incomplete dominance. It's a giveaway. It's a huge giveaway that you're dealing with incomplete dominance. Then an example in humans is the idea of, or is the condition known as familial hypercholesterolemia. So this is an inherited trait, and this is the one that's inherited in a dominant fashion. But if you're heterozygous for this, you have a high level of cholesterol, but if you're homozygous, you have a very high level of cholesterol. It is a dominantly inherited trait, but in this case, the heterozygotes do actually have a trait separate from the homozygotes, and homozygous dominant is not a fatal condition as it is in some of the other dominantly inherited traits that we looked at. What this has to do with is receptors on the surface of your cells that capture the cholesterol particles called low density lipoproteins, or LDLs. These are the dangerous cholesterol particles. Because if you have too many of these in your bloodstream, they tend to stick to the inside of your arteries where the arteries are narrow, and will ultimately wind up in clogging it and preventing blood flow, which leads to heart disease and a heart attack and stroke. So having receptors for capturing these particles is kind of important. So if you are big H, you make appropriate levels of receptors and you sweep the cholesterol out of your bloodstream. If you're heterozygous, you have a reduced number of receptors, but you are able to capture some of the cholesterol. So you have moderate levels of cholesterol in your bloodstream. If you are little h, then you have no receptors and you have extremely high levels of cholesterol. I think I got this around the other way when I was talking in the previous slide. Sorry about that. So this is an inherited condition, and you can typically tell whether you have this allele in your family by looking at what individuals in your family have died of. And again, you just need about 3 generations of family history to find out. If you have a family history of people dying young of heart disease and stroke, then the chances are really good that this allele is part of your family's genetic makeup. Does it mean that you need to run out crying, I'm going to die of a heart attack or a stroke? No, because there are ways of dealing with this. Exercise can reduce the amount of cholesterol in your bloodstream. Medication can help. Lifestyle is basically the answer here. You don't have to be the victim of your genetics. And in fact, you shouldn't consider yourself to be the victim of your genetics, because you are more than just the sum of your genes, as I've mentioned before. Then in the case of the ABO blood system, you have a combination of 2 situations that lies outside of Mendelian inheritance. So Mendel proposes that there are 2 alleles for every gene, but here we've got 3 alleles, what are referred to as the big IA. So you've got big IA, which is referred to in the book as A, big IB, which is given the designation B, and little I, which is given the designation O. And you ought to be able to guess what the relationship is between these alleles. Big IA and big IB are both dominant to little I. But are codominant to each other. And it's this notion of codominance that is the interesting thing here. That's the other thing that lies outside of Mendelian genetics. So Mendel would say, again, one trait is always dominant over the other trait, but big IA and big IB are not dominant over each other. They are dominant over little I, the O allele, but they are said to be codominant to each other. What that means is that they are equally expressed at the same levels. So this is not dominance, this is not incomplete dominance as we saw with the snapdragons, this is codominance. And as the note says here, it refers to the presence of 2 sugars called the type A sugar and the type B sugar on the surface of red blood cells. So if you are big IA or big IA little I, you produce the type A sugar. If you are big IB or big IB little I, you produce the type B sugar. No mystery there. That's exactly what we would predict under Mendelian genetics. But if you're big IA, big IB, you make both sugars and you make both sugars in equal amounts. This is the idea of codominance. Both are expressed to the same level. One trait is not dominant over the other. If you're homozygous little I, you make neither sugar. Now, why should that be important? Because you make antibodies against whatever sugar you don't make. So if you are type A, you make antibodies against B. If you're type B, you make antibodies against type A. If you're AB, you don't make antibodies against either sugar because you've got both of them. If you're type O, you make antibodies against both because you're not making either. And that determines what blood you can receive as a blood recipient and also as a donor. So type O is universal donor. So I've got that. I need to spell correctly, don't I? So type O blood is considered to be the universal donor blood. It can be given to anybody because remember, again, you're not making any antibodies against the A and B sugars because you are making antibodies against both, but you don't have the sugars on the surface of your cells. So your cells can be given to anybody. If you're AB, you're the universal receiver. Because you're not making antibodies against either sugar because you've got both of them. Type B, you can receive B, O, and type A, you can receive A or O. Now, if you're thinking about the RH, this is called the rhesus factor because it was first discovered in rhesus monkeys. We happen to share this. And this is a simple dominant recessive trait. So this is strictly Mendelian. So if you know your blood type, my blood type happens to be O positive. That means I'm type O, but I'm Rh positive. So my blood is not the universal donor blood. That would be O negative, because you would be making, you're not making antibody, or you don't have the type A sugar, the type B sugar, or the Rh sugar, because the Rh sugar isn't, the Rh is another sugar. So the universal receiver would actually be AB positive, because that's not making, an AB positive individual is not making antibodies against any of the three sugars. So it has consequences, but again, this is an inheritance pattern that is something that is outside of Mendel's two laws. Then Mendel also says that one allele gives rise to one phenotype or to one trait. That's not necessarily always the case. In the situation of pleiotropy, a single allele gives rise to multiple phenotypes. And this is very easily illustrated with sickle cell. So individuals who are homozygous for the sickle cell allele have the sickle cell condition. that means that their hemoglobin molecules are abnormal, and instead of being individual hemoglobin molecules, they stick together in long chains. The presence of those long chains inside the red blood cells causes them to change from their normal, what is referred to as a biconcave discoid shape, think a butterscotch candy, into its characteristic sickled shape. So already we've started to talk about multiple phenotypes. Those red blood cells now can't transport oxygen correctly, nor can they pass easily through the tiny little blood vessels called capillaries, which means that the blood flow tends to be restricted or in some cases blocked. That leads to tissue damage in the extremities, like the fingers and toes, because of lack of oxygen. But it also leads to tissue damage and organ damage, and particularly brain damage, because of the lack of adequate oxygen supply. At the same time, the red blood cells get turned over more frequently. We turn over our red blood cells about once every 4 weeks completely. But these red blood cells that are sickled don't last as long, and they get turned over every 2 or 3 weeks, which means there is a great demand for iron, because iron is at the heart of hemoglobin, and that's where the anemia side of things comes in. If you are low in iron, you are anemic. And so because you're turning over your red blood cells so frequently and trying to generate more of these inadequate red blood cells, you get low in iron. As a consequence of all of this accumulated tissue damage and organ damage, your lifespan is significantly shortened. For the average sufferer of full-blown sickle cell, the lifespan is typically somewhere around 55 to 65 maximum, even with medical intervention, because you simply cannot prevent the accumulating tissue damage. So if you were keeping track there, we talked about 15 or 20 different phenotypes as a consequence of being homozygous for the sickle cell allele and having the sickle cell disease. This is a really classic example of pleiotropy, where you have multiple phenotypes as a consequence of the presence of a single allele. Then another situation is called polygenic inheritance, where a single phenotype is the product of multiple genes. So this would be the flip side of pleiotropy. And there are a number of different characteristics in humans that are polygenic, but the giveaway is that there is a continuum of phenotypes, or a spectrum of phenotypes, going from one extreme to another extreme along a continuum or a spectrum. So when you think in terms of human height, that's a really good example, because average human height or normal human height ranges from around 4'9" through to around 6'4", and there are all sorts of variations in between. And the way that you can tell that it is on a continuum is to plot it out. And I've actually seen a photograph of some boys that were arranged by height at an English boarding school, 1-inch increments into columns, standing one behind the other. And a photographer then got up on a ladder and took a photograph. And if you connected all the columns together, you got this classic bell curve, which looks just like that. So at either end, you have the extremes. So this would be the 4'9" 4'9" and over here would be our 6'4", and then everyone else, the vast majority of us is in the middle here. This is average human height, and there are any number of human characteristics that we could put in here. Skin color is another one that fits into the continuum, where you have very light skin, and there we're not talking about albinism. Remember, that's a separate allele altogether. And then you have really dark skin, and then you have the continuum of skin colors in between. That's the giveaway of polygenic inheritance. If you see a characteristic that has this continuum of phenotypes associated with it, you can be very confident that it is the product of multiple genes. You can't point to a single gene that causes this. It is the product of multiple genes, and typically there are multiple alleles of those multiple genes as well. So that's polygenic inheritance. So this shows the skin color distribution just as much as it shows the height distribution, and here you can see the standard curve. We could plot the same idea with skin color as we've done with human height here. Again, there are multiple human conditions. In fact, it's very unusual for a human condition to be the product of a single gene. The idea of the observation that cystic fibrosis, sickle cell, Huntington's and so forth are the product of single genes. That's very unusual. Most human characteristics, most human phenotypes are the product of multiple genes. Then another thing that throws a twist into all of this is the fact that your environment plays a role. Not only do your genes affect your environment does in fact affect the activation of your genes. I was trying to think of the right word there, and I just drew a blank. And this is no more exemplified than looking at a pair of identical twins. Now, I grew up with a pair of identical twins, and it was very easy over time to see the effect of epigenetics. That's the term that we use for looking at the effect of the environment on genes. So if you happen to be a member of an identical twin pair, you know that your twin and you are no longer identical. And the older that you live, or the longer that you live, the more this is going to become obvious. And that's because even though you share the same genetics, you don't share the same experience of the world. And you are not the product of your genes. You are the product of your genes and your environment in combination. This is an argument known as the nature versus nurture argument. And this is an old one. So nature is the genes, nurture is the environment. And it's taken many years for people to actually accept that it's not one or the other, it's both. Now, it's very hard to know which is more important. And I've heard people discuss this and say genes are more important than environment, even though they're both working together. I've seen other people say environment is more important than genes. The reality is that it's probably around 50-50. Is that the real situation? I have no idea. I don't think anyone truly does. All we can say for certain is that it's not just your genes, it's not just your environment, it's the two working together that determine who you are. So this is the last break. And then, well, we've got one more section to look at. I forgot that we've got one more section to look at. Boy, this is a long chapter. Okay, so here are our concept checks for this break. Maria has type O blood and her sister has type AB blood. What are the genotypes of their parents? How does sickle cell disease demonstrate the concept of pleiotropy? If you clone some mice, would you expect them to be identical as they age? Explain. See you on the other side of the break.